Swayam Prabha, Digital India, Educated India.
So this is continuing on rotating frames here, and the first problem that we look at today is an observer on Earth. So usually an observer on Earth considers the movement of objects in his or her surroundings from his or her frame of reference. So for example, when we observe some particle which is falling, we would consider that falling particle as a mass which is moving in our frame of reference. And this is usually taken to be an inertial frame of reference. And by inertial frame of reference, I mean that the observer would consider himself or herself to be in a frame of reference that is not accelerating. So it's at rest. And there's no net force that is acting on it. So, but it is not exactly true, since the Earth is rotating about its axis, and considering it as an inertial frame is an approximation. So for most practical purposes, this is a good approximation, and we will see why. But in reality, it's not exactly an inertial frame of reference. Neglecting the interaction of Earth with other astrophysical objects, consider a person at a position r on the Earth's surface. Okay, so now we come to a sub question, part A. Write down the evolution equation for the position r in the reference frame of the person and in an inertial frame of reference. Take the inertial frame to be centered at the Earth's reference. So for this problem, we'll use spherical coordinates. And here our position is given by r vector, and we use 3 coordinates to denote the position. So one is the radius r, another one is theta, and the other angle is phi. So the spherical coordinates, and we'll consider 2 frames, one which is inertial and another which is rotating with the Earth. So you have a rotation rate omega. So our rotation rate of Earth is denoted by omega, and we'll consider 2 frames of reference. One that is stationary, y, x, z, and another one so rotating about x, the z axis with the rate omega. So these are 2 reference frames. So inertial frame is nothing but, let's say there's an observer outside Earth. So this observer could be in a satellite or could be in another planet, which is relatively in an inertial frame. So it's an inertial observer. It's not accelerating. It's observing this position r vector, and for simplicity, let's say he takes the origin from which he measures to be O, and the person who's in the reference frame of the rotating frame, so is in rotation with the Earth. So that is the non-inertial frame or non-inertial observer. Let's say that person also takes the origin to be O. So everyone is measuring from O. The only thing is that here, in one frame of reference, x, y, z are fixed. Another frame is rotating with omega. So we have to find the evolution equation for the position vector r, and let's first do the non-inertial or the rotating frame. I'll just denote this frame as M. capital M meaning moving frame. Since capital R is the position vector, I don't want to confuse it with rotating frame, so we call the rotating frame as a moving frame M, and the inertial frame will denote it as L, which is the lap frame. So in the frame, the non-inertial frame, the rotating frame, if the R vector is given here, and the R vector is something which is independent of time. So the R vector, so for the person who is rotating with the Earth, he or she will look at the center of the Earth, and since they are in a frame of reference which is not rotated, for in their frame of reference, from their point of view, the R vector is always from the center to that position, and since that position in that frame of reference is not rotating, it is fixed. So this R vector is always fixed. Whereas for an inertial observer, this R vector is something which is rotating continuously. Whereas in the rotating frame, you have R vector which is constant. So in the frame of reference which is rotating, call it M, the moving frame, R dot is equal to 0 at any instant of time, which means that R double dot is equal to 0. So this is the non-inertial frame. What happens in an inertial frame? So somebody else is watching us from far away, and they are supposed to find the evolution equation for R. So the R vector or the radius vector is something which is rotating. So the velocity field is actually changing direction. The person is rotating, the velocity field is changing direction. So let's directly look at the acceleration. R double dot in the lap frame, which is the inertial frame. So R double dot can be written as R vector double dot in the moving frame plus 3 omega dt R vector plus 2 omega times R vector dot in the moving frame plus omega cross R. So this is the transformation when we take the same vector R vector and you write it in two different reference frames. Take two different coordinate systems, for example. So one which is fixed, another one which is rotating. So you have this transformation which you have seen in class. The acceleration measured in one frame of reference for the same vector. Since it's fixed, you measure as R. The coordinate system is fixed. You measure R vector and this acceleration with respect to the lap frame, and that is related to the rotating frame to this equation. And we can see that d omega by dt, the rotation rate of the Earth, is almost constant. It doesn't change much with time. So we can say that d omega by dt is almost 0. Next is the acceleration in the moving frame. So that we can say that since R vector is in the moving, the person always sees the position as R and there's no change, we say that R double dot is. So this finally brings us to this equation, and we can actually do one more simplification. R dot, the velocity in the moving frame is also 0. So this gives that R vector double dot, the acceleration in the inertial frame is nothing but omega cross R. Okay. So this is the evolution equation for R vector in the inertial frame. These are the, you can use just this equation, and also it eventually gives the same thing as here. This is in the non-inertial frame. This is the evolution equation in the inertial frame. So we can try to calculate what is this. So R vector, since we are using polar coordinates, omega is actually the rotation rate of the Earth. Day, some numerical value, but it's along the z direction. Since the axis is along the z direction, everything rotating in the z direction. So omega vector is omega times Ez hat, and R vector is nothing but the radius of the Earth times Er hat. So now, in order to do these cross products, one has to omega Ez hat plus omega Ez hat plus capital R E hat. Okay, since omega these are scalars, I'll take it out. So omega square R times Ez hat plus Ez plus ER. So for this, we'll have to represent either ER in terms of EX, EY, EZ, but as I said, we'll work in spherical coordinates in the inertial frame. So we can write ER in terms EZ in terms of ER, E theta, which I've written in the expression below here. So we'll use this in the expression above. So what we get is omega squared R Ez hat plus. So first we get ER cos ER, which is 0. So we don't need to consider that. And then you get E theta cos ER, and that you get minus sin theta. E theta plus ER. Try to imagine how that vector would look like. So this is your R vector, and E theta is like this, ER is like this. So ER cos E theta would be along E phi. So this is your R, this is your theta, ER cos E theta would be along E phi. So this is nothing but omega square R Ez plus minus sin theta E phi. And again we'll do the same substitution. What we get is omega square R sin theta, which is minus and you get cos theta ER times E phi minus sin theta E theta plus E phi. Okay. So ER plus E phi, so ER is along this direction, E phi is along this direction. ER plus E phi be ER E phi. So that should give you, see from here, the ER vector, that vector, and E phi is along. Going inside E phi. So ER plus E phi will give you minus E theta. So it's taken. Okay, so I think here there's a mistake here. E theta plus ER is not actually E phi, it's actually E theta plus ER will be minus E. So this is actually plus, make this plus, and we go back to this ER plus E phi will be minus E. So I'll put this as E theta hat. And next term you get minus omega square R sine square theta E theta cos E phi. So E theta is along this direction, E phi is along this direction, E phi will be along ER direction. So this is the evolution equation. In terms of theta and in terms of E theta and ER, and other. So we can try to look at how this vector looks like for a person who's standing at a position R vector. We have one component which is along minus E theta. So this we have minus E theta, and another component along minus ER. So you can verify that this actually is the acceleration which is going towards the axis. So since this R vector is rotating about the Z axis, so it's an actually R double dot is nothing but the acceleration, which is centripetal acceleration, which is making the person or the observer move along circles, which rotate about the circle, about the Z axis. So this is what we get. So it physically makes sense. And so this is the evolution equation as asked for the the first subpart. So next part is, so if the person is who's standing at position r vector wants to describe the motion of a particle, he or she will consider a set of coordinates centered at r vector. Write down the relation between the accelerations of a body measured in this frame of reference and in an inertial frame of reference. So here the problem is that we have a person who's standing at a position R, and the problem is to this description of a mass m, which this observer is observing from a coordinate system which is centered around him. Okay. So the problem comes from the fact that a person who's an inertial observer need not take the coordinate system to be centered around the observer. He might take a coordinate system which is centered around his own point of reference, or let's say for simplicity, he might take it from the center of the earth. Okay, and the question comes here that the origin of the observer and the origin of the inertial observer are no longer the same, and one of the origin is actually accelerating, this is rotating, it's actually accelerating with respect to the origin of the inertial observer. The question remains the same if the origin is, let's say, placed on the inertial observer itself, but for simplicity, we'll put it at the origin of the point. So the question remains the same, and the analysis remains the same. So one of the origin is accelerating with respect to the other origin. So this is not the standard case where we had considered here. For example, here both the origins are at the same position, and more importantly, one of the origin wasn't accelerating with respect to the other. So the acceleration remains the same. The origin remains the same, and in this part, however, the origins are separated, and one of the origins is actually accelerating with respect to the other origin. So since the origins itself have changed, the way to relate the accelerations as measured in the reference frame of this person and the reference frame of the inertial observer would no longer be the same as the expression which we used previously. So now we will try to see what is the correct expression that one should use. So let's consider the frame of reference of inertial observer, which is centered on point O, and there's another frame of reference which I'll call it x prime, y prime, z prime, and this is the observer at R, and he or she is measuring an object, let's say at a position R prime. Okay, and the inertial observer, let's say she is measuring a position at a distance R from her origin, and the inertial observer is measuring it at R prime from this origin, which is O prime. So now we say that since R vector is equal to capital R vector plus R prime, the question now is how do you relate the accelerations measured? So how do you relate d square R by dt square measured in the inertial frame to d square R prime by dt square in the non-inertial frame? So I'll write down the question. So this is exactly what is written here, but I'll just rephrase because we have written down this coordinate system, and it will be easier to rephrase the question sometimes in terms of our notations. Sorry, it's acceleration vector d square R by dt square in the lap frame as 2 or 2 T1 in the inertial frame or the moving frame. So this is the question, and we'll try to derive the expression for this. So let's start with this expression. We say r dot or dr by dt. Let's start with everything in the lap frame. So any vector you can measure it in any frame of reference, and the lap frame or the inertial frame is what I denote by L. So this is equal to T capital R dt L plus dr prime by dt. So now I take one more derivative. I say d square r by dt square in the lap frame equal to d square capital R by dt square lap frame plus d square r prime by dt square in the lap frame. But we or the information that we have is that we know the acceleration in the moving frame. So we'll have to relate the acceleration of r prime as measured in the lap frame to the acceleration as measured in the moving frame. So this is the standard expression that we have already seen. So once you have d square in the lap frame, this is nothing but d square r prime by dt square in the moving frame plus d omega vector by dt cross r vector r prime plus 2 times omega times r prime plus omega cross omega cross r. Okay, so this is nothing but you have two vectors, which is you have the same vectors r prime, and you are just measuring it in two frames of reference, and the components. So the components, the vector itself remains the same, but since the coordinate systems, for one of it it's fixed and the other one it's moving, so you have this relation which relates the same vector r prime vector to this fictitious forces. So you have the Coriolis force, Coriolis term, you have the centrifugal term, and you have a linear term related to the rate of change of omega. So this is actually r prime dot, and this is measured in the moving frame. So we can make some simplifications here. So we can say that d omega by dt for the Earth is 0. It's almost 0. So for all practical purposes, it's almost constant. So we can remove that. And now we'll substitute this here. So we say d square r by dt square equal to d square capital R dt square d square r prime by dt square. The moving frame plus 2 omega plus dot prime in the moving frame plus omega plus omega plus r. So this is the expression to relate the two accelerations, and we can do slightly more, some more simplifications. This is the term which is the acceleration of the r vector in the inertial frame. So this one we already found previously. So we just use that. We have this. We'll just keep it in this expression. We know that r double dot nothing but omega plus omega plus r. So again we write this. So d square r by dt square. So this is that thing is equal to d square r prime by dt square moving frame plus omega plus omega plus capital R plus 2 omega plus r prime plus omega plus r prime. Okay, so we can see already that This is exactly the same relation as what I wrote here, just that you have this extra term because this r vector is actually accelerated. Because the two origins are shifted, a slight acceleration due to this distance vector which is rotating, and that is the extra term which comes. Now we have the expression for the acceleration for the position measured in the lap frame to the acceleration for the position vector as measured in the non-inertial frame along with these extra terms, and we can write the other way around also d square r vector by dt square n minus omega cross r minus 2 omega cross r prime minus omega cross r. Okay. So this is the expression which was asked. How do you relate the accelerations in the two frames of reference? And this is what we get. So from this expression, we can use it to study, let's say, how does a mass m falls from a height, say, in a frame of reference at a position r as compared to a frame of reference which is outside. So that is the next question. So the next question is, consider the mass m falling from a height h under the effect of Earth's gravity. Neglecting air friction, write down the equations of motion in both the frames of reference. Solve the resulting system of equations. Okay. So the question is now that the observer position r is looking at a mass m which is falling from a height h. And for that person, he would construct a coordinate system centered around him or her with x prime, y prime, z prime being the coordinate axis. This is your z prime, x prime. So x prime, y prime, z prime can be along any direction, but for the sake of simplicity, we'll say that x prime is along the theta direction. Z prime will be along the radial direction, the local normal. And y prime would be just going into the system. So let's say so here it will be the phi direction. So we have x prime, y prime, z prime, and the idea is to try to understand the equations of motion for this mass m which is falling in the reference frame of the observer at position r, and also the reference frame of the inertial observer who is observing it from outside the earth. So we can write this step by step. So to start with, you have d square r. You already have derived expression. I just repeat the expression. Okay. So one advantage, as I was saying, is that once you have the accelerations in terms of one reference frame to the other, one might have information in one reference frame and certain information in one reference frame, certain information in other reference frame, and then you can transfer or you can use this formula to get the missing information in the other reference frames. So, for example, here we know that for under the effect of gravity, you have your mass m, the only force that is acting on it is the acceleration due to gravity. Or here we use the standard expression for the acceleration between two masses and the acceleration given by gm by r square. And the direction is nothing but the direction along the line which is connecting the mass to the center of mass for the other object. So here it's the center of mass for the Earth, which is O. We consider the Earth to be spherically symmetric with the center of mass at O. So we can write this as d square r by dt square. The inertial frame is nothing but g capital M by capital R square. G is small r square because the distance is norm of r vector. Like this E R. Okay. So here G is the gravitational constant, capital M is the mass of the Earth, and now we can substitute this here. What we get is d square r prime dt square equal to minus gm r square er hat minus omega cos r vector minus 2 omega cos r prime dot minus omega cos r. So now we can try to see that we can say that r vector is more or less equal to capital R, the radius of the Earth. So the radius of the Earth is about 6,400 kilometers. So let's say you have a mass m which is falling from a few tens of kilometers. So for all practical purposes, r vector is almost given by capital R. So this is nothing but minus gn capital R square er omega cos capital R minus 2 omega cos r vector. Yeah. So now we can recognize these two terms. So these two terms are the terms which are related only to the physical parameters of the Earth. So here you have omega, which is the rotation rate for the Earth, capital R, which is the radius of the Earth, and m capital M, which is the mass of the Earth. So in standard situations, one would call this the acceleration due to gravity. But you would see that actually in most situations, people only consider this term to be the acceleration due to gravity, even though this term is non-zero. And we'll see why that is the case, but we'll show what happens when we neglect this term. So we'll just do a small digression and then we say how big is this term compared to this term. Let's do that here just to get an idea of what is it that we are supposed to measure when we measure the acceleration due to gravity. So for what follows, I will do what is known as order of magnitude analysis. So in this, I will consider the cross products to be, so there's an angle between vectors, and I would say that angle is almost, it's always, so you have like omega times cos r is like omega r sine theta, and I would say sine theta is of the order 1. So this is just to, it's not exactly correct, but this is just to get an idea of the order of magnitude of the term which is above. So what I'm saying is that omega cos r, I would just take it as the norm of omega twice, so it's like omega square times capital R, the norm of r vector is capital R, and below you get gm by r square. Okay. So this is of the order omega square r cube by gm, and as I said, the mass of the Earth. So we can look at some standard values. I don't have it in my head. So here I have some values here, so which I'll just read out. So capital R is the radius of the Earth, so about 6,400 kilometers. Rotation rate is just 2 pi over 1 day, which is 24 times 3,600 seconds. So 24 hours, 3,600 seconds, and then you have capital G, which is the gravitation constant, which is of the order 6.7 10 power minus 11, and mass of the Earth is 6 times 10 power 24 kg. So if you substitute all this, what you get is that this term is of the order 4 times 10 minus 9. So it's even less than 1%. So for all practical purposes, we can say that G is nothing but minus Gm by R square. But there is a small contribution which is non-negligible, and the physical effect is that you weigh slightly higher the poles than compared to the equator, because you are in a rotating frame and you have the centrifugal force which acts in the opposite direction to the gravity, and the effective weight is lower at the equator than the poles, and you also have this equatorial bulge for the Earth as a consequence of this rotating. As a consequence of Earth being Earth rotating about the z-axis. Okay. So this, so we go back to this equation now. So we just substitute G to be minus Gm by R square Er hat, and we take minus omega cos r. So this gives d square r by dt square, the lap frame equal to d square r prime by dt square, the moving frame I messed it up. D square r prime by dt square in the moving frame equal to, this is nothing but g vector minus omega cross 2 omega r prime vector in the moving frame minus omega cross r. So this is what I'm supposed to get, and we can make for further simplifications. Since this term is much smaller than this term, even for the capital R, which is of the order of 6,400 kilometers, we can say that this term compared to this term is very small. So you can again do this exercise, and for an object which is falling from few hundred kilometers, we will see that this is of the order of 0.01%. So for all purposes, we can neglect this question. So that brings us to the final equation. So at the end, the modification comes from the Coriolis term. The modification of the particle falling in the inertial frame is slightly modified in the moving frame due to this Coriolis term. So an inertial observer would look at it and say that the particle is falling under the influence of gravity. A non-inertial observer, that is us, would look at it and just say it's falling under gravity, but since the observer is rotating, he or she would have to add a fictitious force, which is the Coriolis, and that is what is given here. So now we can go ahead and solve this equation. So before solving this second order equation in time, it's good to take the boundary conditions. So let's take x prime 0, y prime of 0 equal to 0. So for the person who's observing, the mass is just falling at a height h above him or her, and x and y, x prime and y prime are 0 initially. So at t equal to 0, x prime is equal to 0, y prime is also 0, z prime of 0 is equal to h. Now we can say that x prime dot, this is the initial velocity along x prime, y prime dot the initial velocity along y prime is also equal to 0, and same with z prime dot. Initial velocity is actually just falling from a height h, but initial velocity is 0. So these are the initial conditions, and this we can try solving this above equation. So I'll write down d square by dt square of vectors to write down slightly bigger d square by dt square. So r prime vector, we'll write it as x prime ex hat plus y prime ey hat plus z prime ez hat. This is what I've written here, and this we'll write it as a three-dimensional three row column matrix. So it's a column matrix is x y z. So this is what I'm writing here: x prime, y prime, z. This is equal to g. The g is nothing but 0, 0, 0 minus g. So it's only along the local z prime axis. It's along minus z, so that's why you have minus direction. And you have another term which is 2 omega vector. Omega vector cross r prime dot vector. So that is again x dot y dot z. So now what is omega vector? So omega, we know the earth is rotating at the, so this is the z prime axis, the x axis, x prime axis, and the earth is rotating about the z axis in the non-inertial plane. So this z axis makes an angle theta with the local normal, which is what we have chosen the z prime axis to be. So this is your r vector, and z prime axis is the local normal, and this z axis makes an angle theta. So your omega vector along z would have a component along z prime, which is omega cos theta, and the component along minus x prime, which is omega sin theta. So x prime we are taking it along theta direction. So your omega vector is along ez will have a component along z prime, another component along minus ex prime. So it will be omega cos theta, omega ez, omega cos theta ez prime minus omega sin theta ex prime. And this is the same at all instants of time. So even if the observer is moving, the observer always makes an angle theta with respect to the vertical, the z. So this is always the same. So omega and theta we can take it to be constant with time. So this I can write it as x prime double dot, y prime double dot, z prime double dot equal to 0, 0 minus g minus 2 times. So I take cross product. So what I do when I do cross product is I take the first row, I don't consider the first row, I take this times this minus this times this. So for the first row, what we get is I remove the first row and I say this times this, so that's 0 minus omega sin theta y prime dot this omega y dot prime. For second column, I do the same. I say this times this minus this times this, that's minus omega x prime dot. This is the second row. Minus omega x prime dot sin theta minus omega z prime dot cos theta. So last row, we say this time this minus this time this, to get omega y dot cos theta. So this is our governing equation, and we can write it. So since we don't have any explicit x, y, z prime, x prime, y prime, z prime, we have only derivatives with respect to time or constants. We can integrate once into time. So once you integrate, what you get is x prime dot, y prime dot, z prime dot is nothing but 0, 0, 3t y prime omega y prime sin theta minus omega x prime sin theta minus omega z prime cos theta omega y prime cos theta. Okay. So let me okay, so there's a mistake here. Let's check in. So this omega cos theta along z direction minus omega sin theta here. So I'll just do it very fast. So you get the first column you get minus omega. So you get minus omega y prime dot. Second column you get plus plus. Here you get a minus. And sin theta and cos theta also go next. Okay, so this is the expression, and what we see is that now we have to add a constant term to C1, C2, C3 because we have integrated in time, and what we can show is that x1 dot is nothing but minus plus 2 omega y prime cos theta and y prime dot 2 minus 2 omega minus 2 omega times x prime sin theta plus z prime minus h and x prime. So that's right together here also. This is cos theta sin theta cos theta sin theta. So you get cos theta here and sin theta, and you get z prime dot equal to gt plus 2 omega y prime sin theta. So minus gt plus 2 omega y prime sin theta. So just verify with my notes. So everything's good. So this h comes because at t equal to 0, z prime is not 0. So at t equal to 0, you need velocity to be 0, positions to be 0. So only when with z you have a constant c2 which is non-zero, you get this expression. And this expression verifies the initial condition. So this looks like, so this is the equation that we have to solve. And we can see that this term, for example, has x prime and z prime. So if we take one more time derivative in this equation, we get x prime dot z prime dot, and x prime dot and z prime dot are both in terms of y prime. So I would let you verify that what we get is omega double dot prime plus 4 omega square y prime equal to 2 omega gt and sin. So this is the expression for the y prime, and this equation is like an oscillator which is forced by this term. So you get y equal to y homogeneous function of time plus y particular solution. So this is an oscillator which is forced. So you get a homogeneous solution when you put the right hand side to be 0 and the particular solution due to the term on the right. And by using the boundary condition, one gets y prime of t equal to g by 2 omega sin theta t minus sin 2 omega t by 2 omega. Okay. And we can write down x prime also. That one gets g sin theta cos theta t square by 2 plus cos 2 omega t minus 1 by 4 omega square. z prime of t equal to h minus gt square by 2 plus g sine square t theta times t square by 2 plus cos 2 omega t minus 1 by 4 omega square. So these are the evolutionary. So this is the position vector for particle which is falling under the effect of gravity. So in normal Newtonian mechanics, where we assume that we are in an inertial frame, what happened was that we said z prime is nothing but h minus dt square. That was it. So all the extra terms, this term, this term, this term, comes from the fact that we are in a rotating frame, and the Coriolis term is an important term that we have missed to take into account. Okay. So this we can do in order to get an order of magnitude analysis or an approximate idea of how much is the deflection from the standard prediction of uh, the observer being in an inertial frame. We can do simple expansions to say what is the typical order of magnitude of these different deflections. So for this, we take this approximation saying that the typical time scale for the object to fall from a height h is much slower than the time scale of the rotation of the Earth. So the time taken by the body to fall to the ground is much lower than 1 day. So in that approximation, which is quite normal, because if you have an object which is at a few tens of kilometers, we know that it will definitely fall much faster than the day. So with this, what we get is that x prime is of the order of omega square t square, which is a very small number, so we can neglect that. Y prime is g omega t cube by 3 times sine theta plus something which is negligible, and z prime is equal to h minus gt square. Right? Okay. So the leading order contribution comes from y prime. So from this, what we say is that an object falling from height h experiences an eastward deflection of g omega t cube by 3 sin theta. So t is nothing but, so by the end when it reaches the ground, we can replace t also to be 2h over g to the power 3. So this is a typical deflection that one gets when an object falls from a height h. So this looks like a significant number, but actually, since omega is small, what we get is that, let's say mass m is falling from a height which is 2 kilometers, the actual typical eastward deflection is of the order of few centimeters. So for all practical purposes, it's quite hard to uh, capture this drift, this eastward drift. And in most typical situations, what one gets is that the effect of air or some kind of air flow, which would definitely distort such deflections. So the better way to to understand the rotation of the Earth is through this instrument called as the Foucault pendulum, which you can read about it online. So with this, we come to the end of the second tutorial, and we will meet again in the next tutorial, where we'll take up problems related to Lagrangian mechanics, and we'll see why Lagrangian mechanics in many cases is preferred over Newtonian mechanics.